Okay, so welcome back. Now we cover the topic of goodness of fit. So, and it's a bit different, I suppose, than parameter estimation, but it's a next step in our modeling. So once we have estimated parameters, usually we want to verify that the data conforms to what we call the fitted distribution. We've picked a distribution. We said, okay, I think my data is Poisson or normal or whatever. We fitted the parameters. We obtain estimation for the parameters. Now we say, okay, but is the data really following this distribution? Because of course we assume we know the distribution, but maybe we've picked a totally wrong distribution and the data really doesn't conform. So yes, we've obtained estimators or estimates for the parameters, but maybe the distribution is not correct. So we can check this with statistical tests. Okay, and there's many available. So here we are going to focus on the chi-square test, which is very famous and popular. So, but overall, so this slide is overall, such a goodness of fit test would have the null hypothesis be, okay, our data, our observations were generated by a given distribution. And so, of course, here, if you reject that hypothesis, then the distribution you've picked, okay, this given distribution, you have some evidence that it's not a good model. Okay, so you reject that distribution. Now, if you do not reject, just a comment here that you do not reject, it means, okay, the distribution seems plausible. But remember the logic of hypothesis test, not rejecting H0 does not mean you have proven the data actually comes from that specific distribution. It's just that you don't have any evidence to reject the model, okay? But it's quite different than saying, okay, I have proven this is the correct model, okay? So in words, you might say, okay, this model is decent, it's plausible, okay? But again, it's quite different than saying, okay, I know for sure this is the right model. And also, this comes back to a common saying in statistics: all models are wrong, but some are useful. Okay, so reality probably is not exactly Poisson or exactly a normal, or exactly a gamma, but maybe the models are decent. Okay, so they fit decently well. And of course, well, you know this, but statistical tests obviously are not infallible. Okay, you can always make what we call type 1 error. Okay, rejecting H0 when in fact H0 is true. Okay, so it might be that the reality is actually Poisson, but the data you've collected just randomly, even though it was generated by a Poisson, the randomness has made it look like it's not a Poisson, just by a random chance. Okay, and then you run your test and you reject H0 even though it's true. Okay, the easy example is maybe you have a coin that's actually a fair coin, 50% chance heads, 50% chance tails, but for whatever reason you're kind of unlucky, or just the randomness turns out that even if the coin is fair, you get something very skewed towards tails, for example. Okay, you get out of 20 throws, for whatever reason you get 15 tails. Okay, now if you run a statistical test, you're going to reject that the probability of success or the probability of tails is 50% there, because in a sense you were unlucky that even though the coin is fair, randomness has given you a sample that doesn't really reflect the true parameter. Okay, chance of success there, chance of tails. Okay, and okay, that's type 1 error. Obviously, that would be very unlikely. Okay, it's quite unlikely you get 15. Actually, maybe I need to compute this. 15 heads or 15 tail out of 20. It's probably quite unlikely, but I don't know the exact probability. Anyway, chi-square test, you're probably familiar with it, so it's not overly complicated. Let's review it and then see an example. So here, let's assume you have a sample. Okay, assume IID, and you want to test this. H0 is that this data comes from some distribution. Now, that might be a distribution you fitted some parameters to it, but we're going to come back to this in a second. And then H1, the alternative, is just, okay, X does not follow that distribution, so X follows anything else. Okay, so the method is this. You're going to divide the support of x, okay, by support I mean all possible values x takes, in a certain number of intervals. Okay, sometimes we call those cells. Here I call it just interval. K non-overlapping intervals. Okay, here in notation, if you have k intervals, well, the first one you might say goes from C0 to C1. Okay, and then they're non-overlapping. So the second one would be, because C1 is included in the first, then the second one would be an open interval, meaning it doesn't include C1, but then it does end at C2, so includes C2, and then you have C2, you know, I think you get it, C2 excluded, but then C3 included, and so on, okay? Up to whatever, CK minus 1, CK. Okay, so you have K intervals. Now, the chi-square test statistic is this, so that's the test statistic. That's what you compute, and then you see if it's big, you're going to reject H0. You take the number of actually observed observation at each interval. Okay, so observe means, I think observe, we're going to call it NI, so the number of observation in interval I, minus what you expect under H0, okay? Under the null hypothesis that the distribution is whatever this is, how many observations do you expect? Well, how many observations do you expect? It's simply n, the sample size, times what we call pi here, and pi is the probability to be in that interval given the null hypothesis is true. Okay, so probability that x is in the specific interval, you know, maybe I should have written here, I think it's intended, but under H0, right? That x is in the interval, because then of course, if the probability to be in that interval is pi, then, and you have n observations, the expectation of the number of observations in that interval will be n times pi. Okay, so, and then you take the square of that. So of course, if the data does not conform well to your model, what's going to happen is that, at least for some intervals, the observed will be very different than the expected. Okay, if the observed is very different than the expected, it means your model here is not very good. Okay, well, yeah, because you get very far from what you expected under the model, meaning your data does not conform to the model. Now you take the square of this. Of course, you take the square because you know, you want negative values when you take the sum. If one is much smaller than the expected, but another one is much bigger than the expected, if you don't take the square, this is going to cancel out. Okay, so you take the square, and that's it. Okay, and you divide each of those terms. Okay, there's k of those terms for k intervals. You divide this by the expected again. And then that's it. That's the test statistic. Now, there's some statistical asymptotic theory that says that in the limit, okay, if the sample size is pretty large, this whole thing under H0 is going to be a chi-square. Okay, that's why it's called the chi-square test statistic. Now, this is a rule of thumb, but in reality, you want to be careful. You want to pick as many intervals as you can, but the expected number of counts in each interval should be not too small. Okay, so the rule of thumb is pick intervals such that n times pi, so the expected number in every interval is at least 5. Okay, again, that's a rule of thumb, but so it's maybe not perfect, but that's usually what we do in practice. Okay, and the asymptotic, so meaning for n large, the asymptotic distribution of the test statistic, okay, under H0 is a chi-square. Okay, it's a chi-square with numbers of freedom. Here, careful, numbers of degrees of freedom. So this is a parameter in the chi-square. It's k, the number of intervals, minus 1 minus t, and here, careful, minus t is, so t is the number of estimated parameters within fx, the distribution you're testing. Meaning, if we give you, okay, test that x follows a Poisson 10, okay, or Poisson 5, or Poisson with a given parameter that we don't ask you to estimate, we just say, okay, test that it's specifically that Poisson 10, then you haven't estimated any parameters. Okay, you haven't estimated any parameters, so this t here would be 0. But if I just tell you test that the data is Poisson, just Poisson in general, well, first you need to estimate the parameter of that Poisson, okay, from the data. So then you would have one parameter here. And that's actually the example we're going to look at in a second. Now, because under H0, the test statistic, okay, this is a test statistic as distribution chi-square with those degrees of freedom, what you do to run the test is at a given level of significant little alpha, remember this is a small percentage, like typically 5% or 1%, at a level of significant alpha, we reject H0 if the observed test statistics exceed the 1 minus alpha percentile of the chi-square, okay? The logic of that being, well, let's just represent, let's represent the density of a chi-square, okay? Let's call this F of the chi-square with certain degrees of freedom. Now I forget the shape. I think it's something like this, like skewed. Okay, don't quote me on this, but the shape of the chi-square would be something like this, I think. So under H0, that's the shape of this statistic. Okay, so if you take the percentile 1 minus alpha, okay, so I don't know how to denote this, but maybe Q of 1 minus alpha, something like that. This means that the probability to be here, okay, so the area under the curve here is alpha. Okay, so because alpha is a small number, we say, okay, if the test statistic exceeds this, we're in the part of the distribution that's pretty unlikely. Okay, so under H0, it's pretty unlikely to get the test statistic as big. So we reject H0. We say, okay, it's pretty implausible. Now it's not very plausible now that H0 is true because we're so far away in the tail of the distribution. Okay, so otherwise, this statistic is very big, meaning the observed are far away from the expected by a lot. So the H0 is probably false, right? So we reject H0 for big values of the test statistic. And no, just careful, this is always a one-sided test, okay? We reject only for big values because small values, they don't make us reject. Small values here means that actually, okay, you observe are very close to the expected. You don't want to reject in that case, okay? So it's a one-sided test. Okay, hopefully that's relatively clear. Let's just fix ideas with an example. So that's actually a relatively famous example. It's old data, of course, very old, but I find it quite interesting. Okay, you can read a bit more here. So in a short 1946 article, it's actually an actuary named R.D. Clark reported the following numbers. Okay, so in an area of London bombed during World War II, for 576 different small squared areas, and I believe they were all of identical size, so small squared areas with the same area for each. So they recorded apparently the number of bombs, flying bombs, they say, because landed by I'm not sure if it's planes or missiles, but anyway, bombs that were arrived by air. So for every square, we record how many bombs landed. Okay, and those numbers are given in this table. Okay, so we could have then the x is simply a random variable that's counts. Okay, counts something. It counts the number of bombs in any given square. Okay, now just let's make sure we understand what this table is saying. We're saying, okay, number of flying bombs per square, so 0, and then 229. So for 229 squared areas, 0 bombs were landed. Okay, and then for 211 small squared areas, 1 bomb landed. For 93, 2 bombs landed, and so on. Okay, it gets more likely. Not many areas at 3, and almost none at 4, and only 1 at 5 and over. Okay. By the way, I think I forgot. Oh yeah, I forgot to write it here. 5 and over, but there's only 1, and it was actually not 5. It was apparently 7. Okay, if you look at the actual data, it was actually 7. So in one area, 7 bombs landed. So you see, this total would be our sample size, okay? Because here we model X, the number of bombs in one given square, okay? So we have, in total, we have 576 given square, okay, which is the sum of all those numbers. Now here, test the hypothesis that X is Poisson. Now, I forgot, I should have given you some alpha here you know, test this at whatever. Let's say alpha equals you know, 5%, but it doesn't really matter because we'll see that whatever alpha is, you know, we're not going to reject. Oh, sorry, spoiler, we're not going to reject. Okay, so let's do the calculation. Okay, the sample size is 576. Careful, that's not the number of bombs. Okay, it's the number of squares. So H0 is the sample is Poisson, but with unspecified parameter. So first we need to, because we want to test it's a Poisson, but Poisson with what parameter? Now, if we want to test it's Poisson, the best we can do is grab the MLE estimator of the Poisson. Okay, so we estimated it's of course just a sample mean. Now here, to actually compute it, you actually needed this 7. Okay, I forgot to give it to you, because you need to find the mean of those, the mean of the x's. Okay, and again, careful here, x is the sum of the number of bombs per square. Now, for 229 squares, the number of bombs was 0. For 211, it was 1. For blah blah blah. Now, for 7 squares, it was 4. Okay, and then yeah, I suppose yeah, and then this is what I forgot to say. There's what was 1. It was not 5. It was 7. Okay, so if you count all of this, you're gonna get 737. Sorry, 537, and 537 is the total number of bombs landed. Okay, and then yeah, out of n, which is 576. So you get the estimator for lambda, which is then, I don't know the exact number, but slightly less than 1. Okay, now because we have this, we can build the expected number of well, bombs. Sorry, the expected number of observations per interval. Now, what are the intervals here? Remember, you try to break the support of the random variable x, but here it's a discrete random variable in intervals that in each you want the expected numbers to be at least 5. Now here it's a discrete with only a few values possible, so it makes sense to just say, okay, the first interval is just going to be the value 0. Okay, how many did we observe that at 0 bombs versus how many we expected? How many at 1 bomb versus how many expected? And now here you see, well, the expected probability would be just you grab the probability that x is 0 from your fitted Poisson. Okay, probability x is 0. It's you know, it will be 1 to the minus lambda hat. Okay, okay. I guess I haven't included a calculation here. You can double check for yourself. Whoops. E to the minus lambda hat. Okay, lambda hat, of course, being this thing. Again, same thing. Probability that x is 1. Probability that Poisson with parameter lambda hat is 1. Okay, times the number of observations. You get this. Point here is that if you get to 3, there's still a relatively large number, 30. But then for 4, 5, 6, the numbers get very small. So the last interval, you just group everything that's 4 and above. Okay, everything that's 4 and above. And now you get your observed, how many you actually saw with your own eyes, and how many you expected, and then you're ready to compute this part of the test statistic, observed minus expected, squared divided by expected. Okay, you do this, you do all of them, and then you sum all of them, because of course the test statistic is the sum of all those terms. Okay, and here you get to a number that's this, and you see it's actually, if you look like qualitatively, it's actually remarkably close to a Poisson, right? Because 229 observed versus this expected, 211, okay, actually 211 expected, 93, okay, 98 something, 35, 30, 8 something. It's pretty close, at least intuitively, it looks very close. And you get this, the test statistic. Now, here we have 5 intervals, 1 estimated parameter, and there's also the -1 that's always there. So you get that you need to use the chi-square with the 3 degrees of freedom. Okay, now this chi-square you can look in a table, or you can just use R. You're gonna get to a 95 percentile is this 7.81. Okay, and you see that's much bigger than what you actually observe. Said otherwise, the test statistic is much smaller than the critical value, so you do not reject. Okay, you do not reject. And what I said before is that, you know, if I had used a 90% percentile, I still would have had the number much bigger than this. So with 90%, with any really reasonable alpha, you're gonna not reject. Okay, so you never reject. Okay, so you do not reject, which makes sense. As I said, the data seems to conform pretty well to a Poisson in this case. And yeah, I went a bit fast maybe, but I think those are, I kind of skipped those calculations, but you can verify them for yourself. Of course, it's a bit tedious to do all of that by hand. In reality, you do that you do this in R or any other of your favorite softwares. Okay, that was the main thing to cover. Now there's just one slide about the Kolmogorov-Smirnov test. So let's just cover it conceptually. I don't really have an example here. I think maybe later we'll see an example. And this is also quite tedious to do by hand, so it makes more sense to use this in R. But at least conceptually, what is this test? It's another goodness of fit test. So it also has the null hypothesis, that H0 follows a certain distribution, and then H1 is that it's any other distribution. So and it's also very popular. By popular, I mean, used a lot. So conceptually, it measures this, the absolute difference between the empirical CDF of your data and the fitted distribution. So the test statistic is this thing here. Now, let's just explain a bit. Let's start, maybe this is the easiest. Fx is, as before, what you think what the distribution you've picked to do your fitting. Okay, what you think the distribution is. Then Fn is the empirical CDF, the empirical cumulative distribution function of your data. Now recall, this is easy. It's a function, okay, but you look at your data and the function evaluated at any t is just the proportion of data points smaller than t, okay? So you count how many of the observations are smaller than t, you divide by n. So the empirical CDF is really the observed CDF, if you will, okay? At any point t, what's the proportion of my data that is smaller or equal to that t? And so here you take the difference between the two in absolute value, okay? So how large is the difference? And you take, okay, this technically is the supremum, but don't worry about supremum as a technical mathematical definition, but don't worry about supremum too much. Just consider this to be the maximum, okay? So how big is this difference? Over the whole support, okay? So over the whole support of the random variable, you take those, look at those differences, take the very max one, the very biggest one, that's your test statistic. And you see, if your data doesn't conform to the fitted distribution, this difference would be big, okay? Because there would be a huge difference. If your model is bad, there would be a huge difference between the fitted distribution and the actually observed distribution of the data, the empirical CDF, okay? So if this test statistic is very big, then you have evidence to reject H0 because the data does not conform to your model, to your fitted model. Okay, so that conceptually, I hope this makes sense. Now, operationally, to compute this again by pen and paper, it's not hard. It's just a bit tedious. Maybe I'll say a word on that. But just let me make sure I've covered everything here. Yeah. Okay, and just another point is that the null distribution of test statistics is a bit complicated in the sense it's not like a nice neat distribution like that we're familiar with, like the chi-square or a normal or anything like that. So because of that, usually you rely on a package or in R, this test is actually implemented. It's called with the function KS test. But I'll come back to this at some point. I'll actually go in R and show you how to use it. For pen and paper question, if there's a question like that, I would give you the critical value, okay, to use. But just to illustrate a bit more what this represents, maybe visually, visual representation would help. Let me just draw something here. So do I have, okay. Maybe let me just add something here. Okay, so let's see that on this, you're gonna put your X values. Now, Okay. So those are the x's. Now you have observed a sample x1, x2, blah blah blah. Now let's first consider the empirical CDF. Let's remind ourselves that how this would look like visually. So let's say that the first data point we observe, well, the smallest data point in our data, let's denote it x bracket 1, okay, the first order statistic, which means just the smallest observation in your actual data. Now let's say it's here. Okay, that's the smallest value you've observed. The empirical CDF before, if t is smaller than that value, of course, is 0, because no data points is smaller than x bracket 1. Okay, so the empirical CDF would be 0. Okay, but now there's going to be a jump at x bracket 1, because at x bracket 1, what's happening? Well, you have one data point, so you have one value out of n, which is equal to this one. Okay, so there's one out of n observations that are smaller or equal to x1. So you have a jump here, and this jump is exactly of size. It's exactly of size 1 over n. Okay, again, because here 0 points are smaller. 0 points are smaller or equal to x1, and at x1 exactly 1 is smaller or equal to x1, which is x1. Okay, but here if you keep going, let's say that the second, for illustration purpose, let's put it here. Let's say that the second smallest, okay, is here. So if you evaluate this function here, maybe I should have put t, okay, to highlight this, looking at a function of t here. Well, here, okay, 1 point, so a proportion 1 over n is smaller or equal to those values, and here the second is observed at exactly x2. So then you're gonna have a jump, okay, from there's a jump, there's a discontinuity. Okay, so from x2 you can say, okay, how many points, what's the proportion of data that are small or equal to x2? Well, there's 2 out of n. Okay, so you have another jump, of course, of same size, 1 over n. Okay, so that would be, and then you can keep going, and so, okay, maybe you have in succession, maybe you have a few points that are close, and well, the jumps should be all of the same size here, but okay, I think you get the idea. Okay, that's an illustration of Fn of t. Now, f, the other one here, f x of t, that's the distribution you fitted. Now, I think I forgot to say, I think we assume continuous distribution here. Okay, fx is assumed continuous, so the fitted distribution would then be a smooth continuous function. Okay, now it would be then, I don't know where it is, but something like this. Okay, this would mean the distribution fits pretty well the data, but let's just say that the distribution fits the data pretty poorly, like maybe it's all over here or something. Okay, now this would be then fx, okay, the fitted distribution. So here again, the test statistic is the largest difference between the two functions. Okay, so largest difference. But what I said is slightly annoying to compute, is just how you would do it. You would look at every single value of the sample, and you would check, okay, at x1, what's the difference? What's the biggest difference? Okay, well, here the difference between x1 and the curve is this interval, and then it's here, this interval. But of course, the biggest one for that specific observation is this one. But then you look at every point. Here, the difference goes from here to here. Okay, and then here, the difference is actually this. Okay, and here the difference is this. Okay, and here the difference is this. Okay, but what's slightly annoying is you need to check the difference between the two functions, you know, just before the jump and then after the jump, because sometimes you see here just before the jump, that's where the difference is biggest. Okay, because at this point, at exactly the point, the difference is smaller. Okay, but sometimes it's the other way around. It's it's the difference between the value at the exact value, so after the jump, and the continuous function here, that is the largest. Okay, Now, for now, don't worry about this test too much, because I'll come back to it when we're going to apply it in ARB. Okay, but hopefully, conceptually, you understand that, okay, it's just the difference between, it's a maximum difference between two functions. If this is big, we have some evidence that the model is bad, okay, that the fitted distribution is wrong for our data, and you reject H0. I think that's all I have to say about this test for now. Okay, so thank you for your attention, and I hope you catch you in the next video. So bye-bye for now, and well, happy studying.